The problem for today is, can a falling object catch up to another identical falling object? This is assuming that there are no other influences on the objects as they are falling. Let's get into it. So let's first imagine two balls held stationary at the same height. You may know already, but if I drop an object, then its vertical displacement over time creates a parabolic shape as it moves faster and faster downwards. So if I have two identical objects that are falling at different times, they will create identical patterns in their fall paths as shown. You can imagine that these are kind of parallel to each other, so they will never meet and therefore the second can never catch up to the first. Even if we consider terminal velocity to be a factor, neither ball will ever slow down, and if they reach the same terminal velocity, of course their paths are always still parallel. In fact, the neat thing is that as long as they both keep accelerating, the distance between them actually grows over time. So how does this parabolic shape eventuate? Well, it all comes from the constant acceleration at the beginning. If we look at the most basic case, where the only force acting on the balls is their weight, and hence their acceleration is just that of gravity, then their acceleration over time looks something like this. Simply a negative 10 meters per second change in velocity at all times. So we know that acceleration is the change of velocity, and we can differentiate velocity to get to acceleration. So therefore we can do the opposite and integrate acceleration to get the velocity at any point in time. Anti-differentiating a constant over t simply multiplies it by t such that we get the velocity at any point in time is negative 10t, which is linear. We can see that this makes conceptual sense too, as integration is the accumulation of many small changes. As I total up those many small changes in velocity, i.e. those many values of acceleration, they add at a consistent rate, meaning we get a constant gradient and a constantly increasing downwards velocity as we move forward in time. Applying this approach again to displacement, we know that velocity is the rate of change of displacement, hence I integrate velocity to get displacement. This gives me the rule half at squared or negative 5t squared for this scenario. This of course is parabolic in shape. We can also see that again, if I accumulate those many small changes, this time those changes get bigger and bigger over time, meaning that displacement is increasing by more and more each time, and the paths get steeper as we go further. This naturally produces the parabolic shape that we know of. Let's then plot out the paths of those balls with their equations of motion. Since in this scenario they are simply translated in the dimension of time, which is the horizontal axis, I can represent their equations in the form negative 5t squared plus bt, where b controls the horizontal displacement of the curve. Of course, as we somewhat discussed before, there is no way to get these curves to cross over, and crossing over meaning that one ball has caught up to the other, as they maintain the separation throughout their paths. What we need to do is produce two paths that look like this, where one curve is wider or skinnier than the other. This is called horizontal dilation and is determined entirely by that first coefficient on the t squared. Unfortunately though, that constant is set in stone if we remember that it was determined by the constant acceleration of gravity that comes about after integrating that twice. So we can't change that coefficient. However, what if we did change the starting position of the second ball? Something we can do by adding a vertical translation using this n constant c. Now if we again drop those balls at different times, the first ball is always moving faster than the second, and of course that means it must catch up at some point. Both balls are falling, yet one has just started falling earlier and hence passes the second at some moment in its motion, as outlined by the intersection of the graphs. We can also do this in another way, such as by giving that first ball an initial downwards velocity, maybe by throwing it downwards or something like that. Of course, after throwing it, it still only accelerates downwards with gravity and creates that similar parabolic shape with the same horizontal width. But it is again moving faster at all points as a result of that initial velocity, and again passes the second ball at some point in its motion. Funnily enough, this scenario is somewhat similar to dropping them from different heights, as if we extend that first ball's path backwards in time, it's now identical to if we had just dropped it earlier. So, giving an object an initial downwards velocity can be mimicked exactly by just dropping it at an earlier point in time, just like the previous scenario. So in conclusion, can a falling object catch up to another identical falling object? Yes, if they are dropped at different heights and times, or if given an initial velocity.